we're going to do some more concentration on sequences for a little bit. I want you to consider this sequence here. It goes 1/2, comma, 3/4, comma, 5/6, comma, 7/8, comma, dot, dot, dot. I have two tasks for you. Come up with a formula that starts at n equals 1. So determine, so this will be A1, A2, A3, A4, etc. Determine a formula for AN, and then determine the limit as n goes to infinity of that AN. So first, let's get a formula for AN. I notice when I look at these, the tops are all the odds. So AN, each AN consists of an odd divided by, and each of the bottoms are evens. Well, the way we typically write odd numbers is 2n plus 1, and the way we write even integers is 2n, like so. Now, this has to work for when n equals 1. So if I take and put n equals 1 in here, I'm going to get 3/2. But I need to start at 1/2. So an easy way to fix this is to change that plus to a minus. Now try it. When n is equal to 1, I'm going to get 2 minus 1 will be 1 over 2. Then when n is 2, I'm going to get 4 minus 1, which will give me 3 over 4. So when n is 3, I'll get 6 minus 1, that'll be 5, and over 6. So this is working out perfect. In fact, if the top is right, I know the bottom is right because it's 1 more. Now to find the limit, you can go and do L'Hopital's rule, but there's really no need in some of these problems. It's very simple. All you've got to do is divide by the highest power of n in the numerator and the denominator. So you go like 1 over n times the numerator, because the highest power of n is 1, and do the same thing down here. And then what's left over in the numerator, you'll have 2 minus 1 over n, and in the denominator you'll simply have a 2. Now when you let n go to infinity, this piece will become 0. I'll get 2 minus 0 over 2, which equals 1, and that'll be the limit. It should seem like that too when you think about it. They are getting closer and closer to 1. So, or like I said, in the past, what we've done is you can change this to an x and this to an x, and do L'Hopital's rule and work it that way. But I don't think it requires such a grand effort. So I'm not promising that for all of these. We'll have a lot of different examples. So most of them focus on what's the limit as something goes to infinity. So try this one. What's the limit as k goes to infinity of k over 9k squared plus 1? And I would be afraid, actually L'Hopital's rule would be a pain. This is an infinity over an infinity style of problem, but taking the derivative of this down here, I don't know that I want to do it. So I'm going to play the same exact game that I did before and divide by the highest power of k. So the highest power of k up here is k to the 1. Now I understand it's k squared in here, but when you pull it out of the square root, it will become a k. So technically speaking, the highest power of k is k to the 1. So I'm going to multiply the numerator and denominator by this 1 over k. Now, of course, the numerator will become 1. And the denominator, when I bring the 1 over k inside of the square root, look what happens to it. It becomes 1 over k squared. And now I'm able to multiply through. I'll wipe out this k squared, but I'll leave a 1 over k squared over in the second spot. So the limit as k goes to infinity, 1 over the square root of 9 plus 1 over k squared. And the limit you can take underneath of the root sign, and you can take it to the top and the bottom separately. As long as all the limits exist, I'll end up with 1 over the square root of 9 plus 0, or 1/3. You can always check these on your calculator. Remember, you can always graph this. Put this in with an x into y1, and then look at the table and see what the values are. Or if you just look at the graph, and you'll see that the graph will start to level off at a height of about y equals 1/3. Now all of the regular limit stuff applies. Like if I have the limit as n goes to infinity, let's say a n plus or minus b n, that equals the limit as n goes to infinity of a n plus the limit as n goes to infinity of bn. I mean, you're familiar with all these. If I have something like a constant times an, I'll be able to pull out the constant. It's unaffected by the limit. Products also work. So if I had like an times bn, I could break that up into the limit as n goes to infinity of an times the limit as n goes to infinity of bn, and then the limit as n goes to infinity of an over bn equals the limit as n goes to infinity of an divided by the limit as n goes to infinity of bn. Of course, there's the usual disclaimers occur too. These are only so good so long as every single one of these limits over on the right side exists. Plus, this one cannot be 0. So, all these limits must exist. All limits on the right side must exist, and the limit as n goes to infinity, bn cannot equal 0. There are other things too. If f is a continuous function, so if I have the limit as n goes to infinity of f of an, that'll be f of the limit as n goes to infinity of an. This is simply the definition of a continuous function. So if f is continuous, we could suck the limit through. And I did that when I did this limit right here. The square root function is continuous, so I was able to bring the limit to the inside and handle it that way. So these are all the standard rules. I don't think I need to tell you them. They all just work. The purpose of this is to show you how we're going to handle some sequences and their limits, and I'm not going to typically do any with a calculator. I want to show you how the different methods we use to do them by hand. So I'll start, and a lot of these do use L'Hopital's rule. So this will serve, I suppose, as a brush up to that process. All right, now what you have is you have an infinity, n is going to infinity, and then this thing here is also going to infinity. So this base is going to infinity, but the numerator is going to 0. You can't just put 1 for your answer, although that may actually be the answer, but you have here an infinity to the 0. An infinity to the 0 is an indeterminate form. that means you cannot decide based on this alone. You have to do some more stuff. So with that in mind, I'm going to do, I can't think of any way else besides L'Hopital's rule. So if you'll remember, that means that I take this limit and rewrite it as e to the ln, the limit as n goes to infinity of n to the 2 over n. And then if you recall, because the natural logarithm is a continuous function, I can take this ln and bring, I can take this limit here and basically reverse, bring the limit to the outside of the ln. Typically, instead of writing e is to something, we write this. exp, I'll know that whatever is left inside will be my exponent. So I have the limit as n goes to infinity, ln of n to the 2 over n. All right, so as usual, we're going to take down that exponent. I've already suggested that the natural logarithm is the slowest of the major functions that we deal with. What that means is this is automatically going to be 0 because the n itself, the polynomial n to the 1 power, will outrun the natural logarithm. You'll see once I use L'Hopital's rule. To use L'Hopital's rule, I will change my letters to an x and hope that whatever I get is a convergent limit. So 2 ln of x divided by x, take the derivative of the numerator and the denominator because I have, if x is going to infinity, this is infinity over infinity. So it's a L'Hopital type of a problem. So take the derivative, look, that n snuck in there. I let x go to infinity, take the derivative. Remember, I put a little L here to indicate when I've used L'Hopital's rule. I'll get 2 over x divided by 1. And you need to know that then this goes to 0 because x goes to infinity. So this all ends up being exp of 0, or e to the 0, which is 1, which oddly enough was the answer that you would get if you knew nothing. If you would have guessed that something like this should be 1, then you would have been right. So that means that forces our problem to also equal 1. Let me see where I'm at in my example numbers. Example 2, so example 3. So another limit as n goes to infinity. And we have the square root of n squared minus n. And the trick that is always used on a problem like this, even if you're going to use L'Hopital at some point, is to multiply by the following fraction. And these are, it's called multiplying by the conjugate. When I multiply the numerators together, I'll have a difference of squares. So the top will do this. I'll have the square root of n squared minus n, but that quantity will be squared, minus n squared. There's a difference of squares formula. And the bottom, n squared minus n plus n. And that'll equal the limit as n goes to infinity. Now let me square that out. When I square that, the square root will go away and the n squareds will cancel, leaving me with just negative n. Now, once again, this is the same game we played earlier. The highest power of n is not 2. The highest power of n is 1. So I'm going to multiply the numerator and denominator by 1 over n. Feel free, if you want to convert to x and change this and do a L'Hopital problem, feel free. I don't think I'd want to deal with that part of it, to be honest with you. So I'll have 1 over n times the numerator and the denominator. The numerator becomes -1, and the denominator, when I multiply this through or distribute it, remember when it comes inside of here, it's going to become a 1 over n squared. So I'll have the square root of 1 minus 1 over n. That's the result of doing n divided by n squared. And then when I multiply over to n, I'll get a plus 1 over here. And now I'm ready to take the limits of the top and the bottom and let n go to infinity. The only thing that's going to affect is this guy right here. The 1 over n will become 0 plus 1. And so it looks like I have -1 over 2. -1 half. Now, for you, check this out. Graph y1 equals the square root of x squared minus x minus x. Put that in your calculator and you'll see that it tends to -1 half as x becomes large. Okay, there's a number of ways to do this. I'm going to stick to the simplest way that I can, and immediately, by now, hopefully you're used to this, I'm going to immediately go to the EXP notation, the limit as n goes to infinity, but then I will put the natural log inside of the limit. And the idea is to force a L'Hopital's rule somehow. Once again, this would have been a 1 to infinity type of a situation, which we can't tell what that is until we do some further investigation. So I'll bring the n out front, but that's not the way I really want it. Well, check this out. I want the natural log of n over n plus 5, that's my numerator, divided by, so I'm not going to put n out front. What I'm going to do instead is put 1 over n out here. That's the same as having an n out front. But now I've L'Hopitalized it. How did I L'Hopitalize? Well, this piece here we can tell is going to 1. The natural log of 1 is 0. As n goes to infinity, the denominator goes to 0. So this is a 0 over 0, so it's a L'Hopital type problem. I'm going to leave a little space, and I'm going to work the continuous version of it. Now, before I actually L'Hopitalize, I want to do one thing. X is guaranteed to be positive because it's going to positive infinity, so I can do stuff like this. I can break the numerator up into ln of x minus ln of x plus 5 all over 1 over x. Why in the world would I do that? Well, it's going to make the derivatives easier than a quotient rule. Now, if I use the quotient rule, honestly, is not going to be that bad, but I'm going to avoid it nonetheless. I think I pay for it later on, though. So the derivative of the numerator, that's easy enough. 1 over x minus 1 over x plus 5. The denominator will be -1 over x squared. Let's see how bad this gets. What I think I'm going to do is make this one fraction. And it's not hard to do that one. X plus 5 minus x will give me 5 over x squared plus 5x. And then I'm going to flip this part here. I'll get times -x squared over 1. I'll put this negative 5x squared in the numerator, and in the denominator I'll get x squared plus 5x. Now, you should be able to tell this is going to end up being negative 5, but because I could just simply divide out the x squared from both numerator and denominator, and if I do that, I'll get negative 5 over 1 plus 5 over x. Or we could L'Hopitalise, or we can use L'Hopital some more if you really want to get it to what it is a very obvious limit. So I'll use L'Hopital again since it's a negative infinity over infinity. I'll get negative 10x all over 2x plus 5. Check again. It's still an infinity over infinity, so I'll do a L'Hopital again. This time I'll get negative 10 over 2. And, well, I guess we can see what the answer is going to be. This will be negative 5. I don't need the limit anymore. I can drop it. Actually, probably I should have dropped it by now. And I can simply rewrite this answer as e to the negative 5. That's a tiny number. Graphing would have been a weird thing to try to figure out because this number is extremely small. Let p of x be a polynomial and let, well, I don't need to do anything else. Then I can give you some limits. If I have a polynomial divided by e to the x, guess what? E to the x always wins this and you get 0. The reason for that is because a polynomial, this will be an infinity over infinity situation. I can differentiate the polynomial as many times as whatever degree it is. Say it's degree n. If I differentiate n times, I'll get this complicated number on top, but it will be a number. It'll be divided by something that's going to infinity, so that will end up being 0. Similarly, if I have e to the x in the numerator, this thing will equal infinity. Basically what I'm saying is that e to the x is a faster rising function than any polynomial. And they have their analogs for natural logarithm. Here, if I have p of x versus the natural logarithm of x, p of x wins this battle because the natural logarithm of x is the slowest moving function of all of your functions. And the reason why this is not hard to see why I would do this. If you L'Hopitalise and do 1 over x, and then you're going to get whatever this is, it really doesn't even matter if the only thing that would matter is if p of x was a constant. If it's not a constant, then when you take its derivative, there'll be something left down there. Well, the 1 can stay in the numerator, but the x can join that thing down there to give you 0. This works for n also as well. If it works for x, if it works for a continuous variable, that forces it to work for n, which is called a discrete variable. So now let's do the limit as n goes to infinity of n over e to the n plus n. And now I can make use of whatever the rule is I showed you and rewrite this in the following way. I'm going to divide top and bottom by e to the n. And now, according to the thing I just showed you up here, I'm looking at this right here. This is like n to the 1 power, if you will. This is this particular rule here. And I'll end up with 0 divided by 1 plus 0, or 0. Now, obviously, if they give you a natural log that's broken up, you probably just even if you didn't know anything else, you'll put it back together. And now, because the natural logarithm function is a continuous function, I can bring the logarithm outside of the limit, or bring the limit inside of the logarithm. As before, I'm not going to appeal to L'Hopital, although it's a very easy L'Hopital problem. If you want to start differentiating and you leave it as an n, I don't care. But for me, I can't snub that technical aspect myself. But I'm not going to do L'Hopital anyways. I'm going to divide by n cubed in the numerator and denominator and end up with. So if I divide n cubed by n cubed, I'll get a 1, and I'll get a 1 over n cubed. Same down here, but I'll get a 3 plus 10 over n squared. Well, this is easy now. The 1 is fine. I'll get plus 0. And then I'll get 3 plus 0. That looks like 1/3. Oh, look. I'm going to leave this in too, I think, because it's educational. This happens a lot to students. I completely forgot about that guy, didn't I? This is the natural log of 1 plus 0 all over 3 plus 0, which is the natural log of 1/3, or if you'd like, negative natural log of 3. Either one of those is fine with me. Here I have 13 to the n all over 13 to the n plus 4/3 to the n. I think what I'm going to do here, well, the highest power, I would say this is the biggest thing. 13 to the n is more than 4 over 3 to the n. So I'm going to divide everything by 13 to the n. So I'll have 1 in the numerator, 1 over there, and then I'll have 4/3 to the n divided by 13 to the n. And I believe 1 over 1 plus, I'm going to put these together in here, and I'll get 4 divided by 39 to the n. Now, since this number inside of here is less than 1, greater than 0 though, this piece right here will go to 0. So I'll end up with 1 over 1 plus 0. And that'll equal 1. This is one I would feel really weird about this answer, just because I don't like the looks of it to begin with. So what do I do to convince myself that I have the right answer? Well, the easiest thing is to get that calculator out and see if it agrees with you. So I guess what I'm going to do is clear my y1, and I'm going to copy this, but I have to use x. So you go 13 to the, oops, that was a bad move. 13, where's my exponent? Oh yeah, the character. 13 to the x, divide, now you need parentheses around what we have down here. 13 to the x plus, and then I'll need little parentheses again, 4 divided by 3 to the x. And then we go ahead and finish the parenthesis. I don't really care about the graph so much as the table, so let me take a look at the table. I don't really care where it starts. Let's just take a look and see what these values are. I need the numbers to turn out to be close to 1. Ooh, error. Probably too big for the calculator to handle. All right, I guess we will start it at 1, see what happens. Well, the calculator runs out of the ability to do it pretty quickly, but I think I'm pretty satisfied that it'll end up being 1 like my answer. So I'll go ahead and circle there. Now this is an interesting one. I think let's take a look and see what happens here. Remember, this is 1 over e, so the numerator here, this is going to 0. This piece here means that's going to 0. Actually, you should know what this is. I think I'm going to leave this. You know from a previous class that sine of something going to 0 divided by the same thing going to 0 ends up being 1. I will leave that to you to look it up from Calculus 1. It was one of the first limits that they ever used the squeeze theorem to prove. You can use L'Hopital's rule. There's nothing wrong with it. And I'm not trying to be tricky or anything like that. I'm just saying that you can change this to x and start going to town on L'Hopital's rule. One last topic in here are sequences referred to as geometric sequences. You probably in your lifetime have heard of arithmetic and geometric sequences. Arithmetic had what they call a common difference and between terms, and then geometric sequences have a common factor between terms. So these things are going to take this format. There'll be something like r to the n power, where n will range from 1 to infinity. So the limits are easy. Like if r equals 0, then the limit would of r to the n just simply equals 0 because every term in the sequence is 0. If 0 is less than r is less than 1, then the limit as n goes to infinity, r to the n equals 0. Anything smaller than 1, when you raise it to higher and higher power, gets smaller and smaller and smaller. That was a topic covered in Calculus 1. So what I can do here is I can put this line under that, and then we don't have to have this as a separate case anymore. So the other case here, with positive r that is, let's take a look at r greater than 1. Then the limit as n goes to infinity, r to the n will equal infinity. Very interesting. If r is greater than 1, immediately these explode. But if r is less than 1, they don't. R equals 1 should be no surprise to anyone. Every single term of the sequence is 1. And then with r negative, just remember then that r will equal -1 times the absolute value of r. And then we'll work with it that way. So let me do an example. The limit as n goes to infinity of 0.99999 to the n equals 0, while the limit as n goes to infinity 1.1 to the n will equal infinity. The reason why is because this base is less than 1, this base is greater than 1. What will happen with something like this then? I'll rewrite it as -1 to the n times 0.99999 to the n, and this is just going to oscillate. You'll have a negative term, then a positive term, a negative term, positive term, but the oscillation won't matter because this piece right here is going to 0. You can oscillate up and down from 0, And basically what it'll look like if you graphed it, it's still going to 0. This still equals 0. But you'll have something like this. In the early stages, they'll vary from the x-axis a lot, but then they'll start closing in on it and being very close to y equals 0. One note, though, I could not have broken this up into two limits, because if I tried to do this, that limit does not exist, because if you remember, that sequence goes -1, 1, -1, 1, -1, 1, and that does not converge. It doesn't come close to either -1 or 1, although it does touch them, but it doesn't come close and stay close to one or the other of them.